Hello, in this video I want to take a look at Taylor polynomials again here, nth degree Taylor polynomials, but doing it in a different way. Actually, this is the way that I think of them myself. The text is doing all this stuff with integrating by parts and keep generating the next Taylor polynomial from the previous integral that they just had, but it's possible that this was taught to me when I was a student, but I don't remember it at all. I learned this more recently. But what I understood as a student was I could build polynomials knowing certain bits of information, right? If I know 2 points in the plane, I can come up with a linear polynomial that is the line connected by them. If I knew 3 points in a plane, not on the same line, I could fit a quadratic polynomial in to fit those. That having 3 points is 3 bits of information. A quadratic polynomial is something like ax squared plus bx plus c. It's got 3 unknown coefficients. Well, those 3 bits of information would give me 3 equations that have to be true in order for the polynomial to pass through those points. But it's got 3 variables, 3 unknowns, and I could solve it. I could always come up with stuff like that. Likewise, if you have it doesn't have to just be points. It could be information about derivatives. If I know, well, simple one, if I know a point that a line goes through and the slope that I want it to have, then I could use the point slope form to come up with the equation of a linear polynomial, right? If I had 2 points that I want a parabola to be on, quadratic to go through, and I knew the slope at one of those points, I could find the polynomial to do it. I'd have 3 bits of information to find the 3 coefficients in that polynomial. And so this is what I want to do thinking in terms of Taylor polynomials. So here we go. So suppose I have a function, f of x, and I want to find a polynomial function, call it Tn, which is the same thing we've been calling them already, that has the same function value as f at x. It has the same derivative as f at x, and the second derivative, the third derivative, all up to the nth derivative. They all match. So there's all these things. I want f of 0 to be Tn of 0. I want f prime of 0 to be Tn prime of 0. That is, the polynomial function should have the same derivatives as f and the same function values of f at 0. Now, I'm choosing to do this at 0 just for the simplicity of the notation. I can then move it wherever I want. We'll discuss how that happens in a bit. But here we go. This is, how many? 1, 2, 3, okay. So, first derivative up to nth derivative, there's n equations right there, plus this first one. This is n plus 1 bits of information, okay? And a polynomial, Tn, which is an nth degree polynomial, will have n plus 1 coefficients, right? It has the constant coefficient, first degree, second degree, third degree, all the way up to nth degree. So it has n plus 1 coefficients, and I have them spelled out here, A0, A1, A2, up to AN. And this is going to, okay, so Tn equals this, which is leading me to the equation that Tn of 0, which would be this, equaling A0, that has to equal F0. So I have a very simple equation that A0 has to equal F of 0. Right? Now looking at all these other, for some reason, this is not, so I want to see if I can adjust something a little bit. Nah, I'm going to run out of space. Never mind. So each information each thing that I have saying that I want the first derivative of t to equal the first derivative of f, now I can figure out what the derivative is. So I know that Tn is this. When I take the derivative, the constant goes away. This just becomes an A1, that's that right there. And then there's a 2a2 times x, that's right there, a 3a3 times x squared, and so on. So this is the derivative of that polynomial. If I plug in 0, look what happens. All of these go away, and I'm just left with a1. So I know that the derivative of Tn at 0 is just that coefficient in front of the linear x, right? And I want that to be the first derivative of 0. So likewise, the second derivative, taking the derivative of this thing now, the constant goes away. I get 2a2, I get 2 comes down to join that 3. So 3 times 2a3 times x, and then 4 times 3a4 x squared, and so on. I take the derivatives. Plugging in a 0, I get that the derivative at 0 is now 2 times a2, and I need 2 times a2 to equal the second derivative of f, which tells me that a2 has to equal f double prime of 0 over 2. And each time we take the derivative, one more constant goes away, and then you get the next constant. But then it's been multiplied by things, right? First it was multiplied by 2, then it was multiplied by 2 times 3. The next derivative would be 2 times 3 times 4. The next derivative would be 2 times 3 times 4 times 5, and so on. So we would get the following, that 3 times 2, a3, is going to be the third derivative of f. So a3 has got to be the third derivative divided by 3 factorial. Likewise, the next one, 4 times 3 times 2, a4, is going to be, the notation isn't right here, that should be fourth derivative. Maybe I can change that real quick. That looks better. 4 times 3 times 2 times a4 equals the fourth derivative of f evaluated at 0. And so a4 is going to be that fourth derivative divided by 4 factorial. And so on down the line, all the way down to the nth one here, where n factorial times a to the n equals the nth derivative of f at 0, which means that a sub n is the nth derivative of f at 0 divided by n factorial. And this gives us the Taylor polynomial. It was going to be a0 plus a1x plus a2x squared, and and so the a0 was f of 0, and the a1 was f prime of 0, and the a2 was f double prime of 0 divided by 2, and so on. And so what I get is I get the Taylor polynomial centered at 0. This is exactly what we got using the text's way of doing it with integration by parts. But this is just saying, I want a polynomial and I've got some information, so let me find the coefficients that satisfy all those bits of information and see what it has to be. And what it has to be is the thing that we've been getting with all the integration by parts stuff. Okay. And so lastly, what do I do when I want to center it somewhere other than 0? Well, to me, this has always been, I learned to graph long before graphing calculators exist. So it's like, I know that if you can do something in one place, you can draw a graph in one place, and then you just want to move it over, then all you got to do is replace all your x's by x minus whatever. Okay. So what I do is I say, okay, I want my derivatives to be what's happening at b. So f of b, f prime of b, f double prime of b, right? Don't plug in 0, plug in b, plug in where you want. Make the polynomial as if it were still centered at 0, but with those different slopes. But then move the whole thing over. And by moving the whole thing over, I'm just saying, take all the x's and replace them by x minus b's. So I wasn't evaluating the slopes and things at 0. I was getting them at b, but then I'm moving it over so that everything's actually happening at b. And so this is the general Taylor, nth degree Taylor polynomial centered at b. But the way I would calculate it is same as if I did it at 0. And it seems entirely appropriate that we should end this video with a typo, because I just noticed that this x minus b here should be raised to the n power, right? You got it to the first power, the second power, to the third power, the fourth, the fifth, and so on. And the last one should be x minus b to the n. So let's make it so. There it is. It was hiding. X minus b to the n. There you go. A different way of thinking about Taylor polynomials.